Hello everyone and welcome to another lesson. In today's lecture, we will be talking about sampling and sampling distributions. And this is chapter 7. Today's learning objectives. First, we will be talking about definitions pertaining to samples, distinguishing between different sampling methods, concept of sampling distribution, central limit theorem, and finally, we will be talking about computing probabilities related to the sample mean and the sample proportion. Right, so these are the learning objectives for this particular chapter. And now let's look at the whole lesson breakdown. So we have 4 sections. So the first section we will be looking at sampling. The second section we will have a brief introduction into survey. And the third section sampling distribution. And the fourth and final section is sampling from finite populations. So the sections 1, 2 and 3 we will be looking at it briefly. However, the core of this particular chapter we will be looking at sampling distribution. So this section 3 is the most important section of this particular chapter. But before that, we are talking about sampling distribution. So we need to have a basic understanding about sampling and about surveying, right? So let's have a look at sampling first. Right, so the first question which arises is, why do we sample? Now, we are doing statistical analysis. So, if we are to consider the whole of the population that we are interested in, sometimes we might not be able to do a statistical analysis or gather data from the whole population. Take for example, you need to figure out the amount of money saved by people in the South Asian region. You want to do an analysis of this. So your population would be the people who are actually working, the employed people in the whole of South Asia, which should be millions. Now you can't go door to door and ask and gather data from all the people who are working, which is impossible. So you would rather take a sample from South Asia and analyze that and then infer about your population. So basically that's why we sample, because selecting a sample is less time consuming and less costly than selecting every item in the population. And analysis of a sample is, as it said, is less cumbersome. It's not as difficult as taking into consideration the entire population, because assume hypothetically you were able to gather all the data for the whole of South Asia, the people who are working, then the issue is the amount of data. Now you have to include this data into an Excel sheet or Stata or whatever it is, some package. You will have millions, rows and rows of data, which will be very difficult and tedious to analyze. But however, having a sample would make that data less, right? So a sampling process begins with this concept known as sampling frame. Basically, sampling frame is the listing of all the items that makes up the population, right? That's what you have to know. Listing of items that make up the population. So that is the sampling frame. So it can be population lists, directories, maps, likewise. If the frame, now this is important, if the frame excludes certain portions of the population, your results will be inaccurate or biased. So this is what's important. When you're considering samples, you have to ensure that all the proportions are taken into consideration, right, of your particular population. Then using different frames to generate data can lead to dissimilar conclusions, right? So here I have 2 videos which I implore you to watch, because both these videos explain about different types of sampling, right? So these two videos, some of these terms might be different to what I teach, but the crux of the content is the same, right? So the second video talks exactly about what I will be talking about, the types of sampling: random sampling, stratified sampling, cluster sampling, and systematic sampling. The first video also talks about this, but it also talks about some additional types of sampling as well, right? So moving on, since we are doing sampling, we have to know that there are different types of samples available to us, right? So you have something called non-probability samples, under which we will briefly look at judgment and convenience sampling. And then you have something called probability samples, under which we will briefly look at simple random, systematic, stratified, and cluster sampling. So first, let's have a look at non-probability samples. So in a non-probability sample, items are included, chosen without regard to their probability of occurrence. That's why you say non-probability. You don't consider the probability of occurrence, right? So if you're not considering the probability of occurrence, well, accordingly, you have two types: convenience sampling and judgment sampling. Two types that we are talking about, right? So if you look at the definitions for convenience sampling, you will see that the items are selected based on the fact that they are easy, inexpensive, or convenient. So now let's have a look at judgment sampling. You get the opinions of pre-selected experts, right? You get the opinions of pre-selected experts. Now, what do these definitions tell you? This tells you that this sampling type is biased, because, for example, in convenience sampling, the person who's gathering the data would select whatever the list from the sample frame. The person who's gathering the data would select whatever is easy for him, right? And that sample might not actually represent the population properly. And this goes for judgment sampling as well. So this here is biased type of sampling, these two non-probability samples. So in the case of probability samples, you are taking the samples based on known probabilities, right? So there are four types. The first one is simple random sample. The second one is systematic sample. The fourth one is stratified sample. And finally, we will talk about cluster sample. So first, let's have a look at what this simple random sample is. Simple random sample, from the name itself, you should understand you're randomly selecting items, right, from your population. So every individual item from the frame, when I say frame, think about the population, right, has an equal chance of being selected. Now, when I use the word population, right, don't think of the population of Sri Lanka. No, whatever the population that we are interested in. It can be that we are analyzing about different types of viruses, right? So then your population would be all the types of viruses that are available, right, in the world. And your sample would be, you would consider certain types of viruses, right? So in the case of getting back to our lesson, in the case of simple random sample, why do I say this? Every individual has an equal chance of being selected, because we are randomly selecting people. So assume that there are 10 people, you are randomly selecting, say, 2 people, right? So out of all of those 10 people, you're only selecting 2, right? So the individual being selected, all these 10 individuals being selected have an equal chance of being selected. And the selection may be with replacement or without replacement. So you can select from the 10 people 2 people, and you can take them out and then again select 2 people, or else you can put the 2 back into the population and again out of the 10 you can select another 2, right? So that is the difference between with replacement and without replacement. And samples obtained from table of random numbers or computer random number generators. So in the case of selecting randomly, what you would do is ideally there's a table of random numbers, or you can use the computer to generate these random numbers, because then these numbers would be actually random, right? It would be correct in order to say whatever number that was chosen was not chosen based on logic, but it was based on randomness. Right, so this is simple random sampling, where basically you choose your sample based on random numbers that are generated. Very simple. Then you have something called systematic sampling. So what is this? So here you decide upon your sample size, let's say simple n, and then you divide your frame of n individuals into groups. So let's say your population is capital N and you decide on your sample as simple n. You divide them into groups such that you divide your population by your sample size, and then you get your groups, number of groups. So for example, think of capital N as 100, and that is your population, and your sample you're considering 10. So 100 divided by 10 would be 10. So there would be 10 groups. Now what you do here is, in systematic sampling, you first randomly select one individual from that first group of 10 people, right? You randomly select one person from that first group of 10 people. Then afterwards, you select every 10th person thereafter, right? That is why I say kth individual over here, right? So k is 10. After you randomly select a person from the first group, say you're selecting the second one, right? Then from the second group, you would choose the 12th individual. Why is that? That is 10 people afterwards. And from group 3, you would choose the 22nd individual. Group 4, 32nd individual. And likewise, it goes. So the randomness in systematic sample only depends on that first group element or item or individual you're selecting. Afterwards, it's every kth individual or every group number, the group size that you selected as k individual you're selecting from each group. So here you have groups, say n is 40, that is your population size, and your sample size is only 4, and because of that your k is 10, right? So you have 10 groups of individuals. So this here is your first group. Your first group has 3, 6, 9 and 10, right? So you select one person, say you select the 7th person. So now what happens, that is the randomly selected individual from the first group, right? So thereafter, since k is 10, you selected the 7th person randomly, then you go and select the 17th person from the second group, 27th person from the third group, 37th group from the fourth group, likewise, because you are selecting every kth individual thereafter. Right, let's move on. Let's have a look at what this stratified sampling is. So just like the previous sampling method, which is systematic sampling, where you divide them into groups, right? In stratified sampling, you also divide them into groups, but these are called strata because these groups, the important term, have some common characteristic. That is the importance or the difference between stratified sampling and systematic sampling. Under stratified sampling, these groups that you are dividing them into have a certain characteristic. So for example, say you want to, like I said, let's take the example that I talked about before. You want to look at the amount of money saved by people in Sri Lanka, let's say that. So you want to do a stratified sampling method. Now you're going to divide your groups into age categories. The people who are in their 20s, the people who are in their 30s, 40s, and 50s. So you see, if you are doing a stratified sampling, the common characteristic, right, would be that age, 20s, 30s, 40s, and 50s. So you divide them into groups, but they have a certain characteristic. Each group has a characteristic. The group of 20s are people, or a group of people who are in between the ages of 20 and 30. The group of 30s are a group of people who are aged between 30 and 40. Likewise, a certain characteristic. Right. So a simple random sample is selected from each subgroup with sample sizes proportional to the strata sizes. And samples from subgroups are combined into one. This is a common technique when sampling population of voters stratifying across racial or socioeconomic lines. Right. So the two second and third bullet points. A simple random sample is selected from each subgroup. Right. So now you divide these into groups, like our example, 20s, 30s, 40s, 50s. And then what you do is, from each group, you select subgroups which are randomly generated subgroups, right? So these are simple random samples. So from the 20s group, you select a subgroup. From the 30s group, you select another subgroup. All of these are simple random samples. And the sample sizes should be proportional to the strata size or the main group size. So if the 20s group have about, say, 100 people, your simple random sample, say, should be about 10. It should be proportional, right? There should be a certain proportion assigned to it. And then samples from subgroups, right? So you have subgroups selected now are combined into one. That is what we do in stratified sampling. So the population, say, is divided into 4 strata, right? It's 4 subgroups like this. And then you're selecting random samples from each subgroup. These people selected in red are the ones who are selected from each group. So the first group, you're selecting 3 people. The second group also, you're selecting 3. Likewise. So then you take all of these and you combine it into one. And that is stratified sampling. Finally, cluster sampling is where you divide the population into clusters, right? Each represents the population. And a simple random sample of clusters is selected. All items in the selected clusters can be used. So here you divide your population into 16 clusters, right? So that each cluster should represent your population. And a simple random sample of clusters is selected. So in this case, you randomly select 3. And then all items in the selected clusters can be used for your sample. So we talked about 4 types of sampling. Now, since we talked about 4 types of sampling, we have to compare these sampling methods. So the simple random sample and the systematic sample are simple to use, but it might not be a good representation of the population, because the population will have different types of characteristics, and these two will not definitely represent the population properly. In the case of stratified sampling, it ensures representation of individuals, but however, it is not very easy to do. It takes a lot of time. And the cluster sample, it is of course cost effective, but it is not so efficient because you need a large sample to acquire the same level of precision. So the larger sample gets, the more data you need, right? So it's not very easy to do as well, this cluster sample. So that is it for sampling. That is our first section. Right, so let's now have a look at this survey, right? The second section. So in this section, we have to evaluate the worthiness of a survey. So we have some questions to ask ourselves. what is the purpose of the survey, right? Why do we do this? Is it based on a probability sample, right? So we have non-probability and probability sampling methods. Is your survey based on the probability sampling methods? And then you have certain errors like coverage error. Have you chosen your sample frame properly? Sample frame is your population appropriately. And then you have non-response error. So people don't actually respond to your survey questions sometimes. So you need to follow up. Then you have measurement errors where if you don't ask a good question, you won't get a good answer. And you have sampling errors, which is the difference between your samples and your population, right? So when you're considering these types of survey errors, that is very important, coverage error or selection error, this exists if some groups are excluded from the frame and have no chance of being selected. So for example, if you consider the non-probability sampling method, you're considering, say, convenience sampling. You're considering people at your convenience. So you're definitely going to exclude certain groups from the frame, right? So there's a coverage error included in that. So, and in the case of non-response error, people who do not respond may be different from those who do respond, right? So some people might not respond to your survey questions and there might be a reason for it, right? So you need to make sure that you follow up on this, right? You need to call them, you need to contact them and follow up and ask them to respond. And then you have something called sampling error, right? So this is the variation from sample to sample. And measurement error. So if you don't design your survey properly or accurately, you will have a certain measurement error. We call it this interviewer's effect on the responders. We call it as Hawthorne effect, right? So basically, if you might have bad questions in your survey or people might not respond and you need to call them and contact them, and there might be differences from your one sample to the other sample, and certain people might be excluded from your population or the frame, right? So these errors you need to be aware of when you're doing a survey. So that's it. That's a very brief introduction into survey and a brief introduction into types of sampling. Now let's get into the most important section, which is sampling distribution. Right. So here I have a video, right? And I want you to watch this particular video because in this video they explain very nicely what this sampling distribution is, right? With a lot of graphics, so you will understand it when you come into my section as well. Right. So sampling distributions. What is this? So sampling distribution is a distribution of all possible values of a sample statistic, right? A distribution of all possible values of a sample statistic for a given size sample selected from a population, right? So it's a distribution of all the possible values of a sample statistic for a given sample size selected from a population. Very important definition to keep in mind. So take an example. You sample 50 students from your college regarding their mean GPA or your average GPA. If you obtained many different samples of 50, that is, you have one sample 1 of 50 students, sample 2, 50 students, you will compute different means for each sample, right? So you have one particular sample of 50 students, this is your sample 1, and you calculate your average. And then you take another sample of 50 students, right? So let's call it sample 2, and you calculate your average, right? So the average as in the mean, right? So the mean here, right, let's call it M1, and the mean here would be, might be the same or might be different. Let's call it M2, right? So likewise, you can have different samples. And what we are doing is interested in the distribution of the means. So we take these means, right, M1 and M2, and likewise let's have n samples so that we have n means, right, Mn. We take all of these means and we look at the distribution. That is what we do here, right, in this particular example. So developing a sampling distribution. Now assume there is a population and the population size, we categorize them into 4, right? So we have 4 A, B, C, D people, 4 types of people. And what we are interested in is the age of these individuals. We call this random variable X. And X can be 18, 20, 22 and 24, right? So we are looking at categories. This category A consists of people of 18, category B consists of people of 20, likewise category C people of 22, category D people who are 24. So let's have a look at summary measures for the population distribution. Now when you're considering that particular example, if you consider only one from each group, right, and if you calculate the mean, you would simply calculate the ages, you add up the ages and you divide it by the 4 people and you would get 21. Similarly, you can calculate the standard deviation and you would get 2.236, right? Now notice here we are calculating the population mean and the population standard deviation, and we only assume that there are 4 people. Right, so then accordingly for these 4 people, let's say the person who's 18, the probability of that person being 18 would be 1 divided by 4, because there are only 4 people. So you understand for each person there's an equal probability, right? So 0.25 would be that probability. So there are 4 people, 1 out of 4 is 0.25. Similarly, you get the distribution like this. You get a uniform distribution. Now consider a sample size of n equals to 2. Now assume that there are more people here for each age category. Now you are considering a sample size of n equals 2. So what do I mean by that? If you take your first observations, you have 18, 20, 22, 24, and your second observation the same. So if you consider this value over here, your first observation is 18, your second observation is 18. And your first observation is 22, and your second observation is 20. Likewise, your sample size is 2, 18, 18, 18, 20, likewise. So if you consider all possible samples, when your n is 2, you would get 16 possible samples, right? And remember we are doing this sampling with replacement. Then you can calculate the mean values for each of these sample sizes, right? So you have 18, 18, the average age or the mean age would be 18 plus 18 divided by 2. You get 18. If you consider this 24 and 22, you calculate the mean value, which is 24 plus 22 divided by 2 is 23. So what you are getting here is, this is a table of 16 sample means, right? So here you have 16 possible samples of sample size n equals to 2. Here you have 16 sample means. Now let's keep that to a side. So let's have a look at the distribution for these 16 sample means. Sample means distribution. Right, let's draw the graph. So you have x bar and probability of x bar. Why do I consider x bar? Because we are considering sample means, right? And you have all the ages here, the average from, so you have the least value is 18, the maximum value is 24, and you have all the values in between. So you mark them accordingly. And now you check what is the probability of you getting 18. So you get 18 only once, and there are 16 sample means. So 1 over 16 gives you a probability of this value, right? It's a certain value. Likewise, for 19, you have 19 two times, so 2 over 16 is 1 over 8, which is a little bit greater than the probability of you getting 18. Likewise, if you plot this particular graph, you will see that the distribution is very much different to the initial distribution. So this is no longer uniform. In our original population, it was uniform. The probability of you selecting one person from the 4 categories of ages was the same, 0.25. But the probability of you selecting a person from the age category for the sample means is different, and the distribution is no longer uniform. So the sample means distribution, you have it like this, and you have your uniform distribution for your population. You notice that sample means distribution assumes a type of normal distribution in this case, but your population distribution is uniform. This is a very important observation. Right, so the summary measures for this sampling distribution. Let's calculate how do you read this? The mean of the means. You're calculating the mean of the sample means, that is this. So you have 18 plus 19, likewise you add up all the values. On all these values represent mean values, and you divide it by 16 because you have 16 sample means, right? So, and you get 21. Similarly, you calculate your standard deviation for the sample means and you get 1.58. So you divide by 16 because there are 16 different samples which are of size 2. So if you increase this size to 3, right, you would have more samples, right? This 16 would increase even further. You would have 64 samples in the case of you considering 3, the size being 3. Right, so comparing the population distribution to the sample means distribution. So in the population you had 4 and your average was 21, your population mean, and your population standard deviation was 2.236, and your distribution looked something like this. But in the case of your sample means distribution with sample size 2, your distribution was very much different, right? But something to note here, your population mean and your sample means, the mean of the sample means were the same. So this is an important observation. Before we get to that, let's talk about this standard error of the mean. Different samples of the same size from the same population will yield different sample means. That is understandable because now you have various samples and you're considering the means of each of these samples, right? So there can be a difference. So this difference is measured by something called the standard error of the mean. And what is the equation for that? That is given by sigma x bar. The sigma x bar is the same sigma x bar which we looked at in the previous slide, which is the standard deviation of the sample means. And that is given by the population standard deviation sigma divided by the sample size, square root of the sample size, right? So if you notice here, as n, your sample size, as it increases, your standard error given by sigma x bar would decrease. That is an important observation. Now, if the population, up to now we were not talking about the distribution of the population. So in the previous example, of course, the population was uniform. But if your population is normal, how would this change? Well, if your population is normal, the mean of the sample means would be equal to your population mean. That is an important observation. And your standard deviation of the sample means would be equal to your population standard deviation divided by your sample size, the square root of your sample size. Or in other words, this is your standard error as well. So this is in the case of the population being normally distributed. Earlier your population was uniform distribution, and you also observe that this is equal. That's what I mentioned before. But this is definitely true in the case of the population being normal, right? That is important. Right, so let's have a look at the Z value for sampling distribution of the mean. So we are talking about, all this time we've been talking about the sample statistic of mean, right? So now we are looking at the Z value. So the Z value pertaining to sampling distribution of your sample mean x bar, this is your sample mean, is given by this equation. This is very similar to what we talked about under continuous distributions in chapter 6. But the only difference is here you have x bar and mu x bar and sigma x bar, because you're talking about sampling distributions of the mean, right? So let's have a look at some of the properties, sampling distribution properties. So mu x bar is equal to mu, and so which means that x bar is unbiased. So you have a normal population distribution. Let's say this is your normal population distribution, and then you convert this into a normal sampling distribution, right? So you have x bar and you have mu x bar, right? So you have your population distribution which is normally distributed, and accordingly you have your corresponding normal sampling distribution, right? So let me explain this a little bit. You have your population from which you derive various samples, and from all those samples you are deriving means, and what you're doing is you're plotting these means, and this is what that plot looks like, the normal sampling distribution. And the mean of the sample mean is given by mu x bar, and if your population is normally distributed, your mu x bar would equal your population mean. It's very important to have an understanding about the terminologies. This is your mean of the sample means, and this is your population mean. These two are equal only if your population is normally distributed. Now, if you notice, as n increases, your standard deviation of your sampling means would decrease. So here you have a small sample size. Now, if your sample size increases further, it would look something like this. So if you notice, your standard deviation of your sample mean has decreased. So let's have a look at an example. You are asked to find a symmetrically distributed interval around mu that will include 95% of the sample means when your population mean is 368, your population standard deviation is 15, and your sample size is 25. Let's have a look at how you find out the answer for this. Right, so how do we go about solving this? Let's first convert this problem into a standardized normal distribution, so that we have Z here and here the standardized normal distribution, and the corresponding mean value would be 0, right? And you're told to find 95% of the sample means around mu, around this value. So the corresponding value of this would be 0 here, and the area under the curve up to this point would be 0.95. Since we are talking about the standardized normal distribution, this area and this area would be 0.025 and 0.025, right? Because when you add these two, you get 0.05, and when you add 0.05 to 0.95, you get 1, which is the total area under the curve. Right. Now, we know that Z equals x bar minus mu x bar over sigma x bar for a sampling distribution, right? When we talked about this. Now, sigma x bar is x bar minus mu x bar over sigma over root n. Now, from this, we can derive that x bar is equal to mu x bar plus z times sigma over root n. Now, why did I derive this? Because now we know the area under the curve. From the table, we can derive what the corresponding z values are here and here. Now, since this is symmetric, we only need to figure out the corresponding z value here, and it will be a negative value because it's to the left of 0, and the corresponding value here, since it's symmetric, would be the same value with positive sign in front, right? And once we figure out these z values, we just have to substitute it to this equation in order to find out the x bar values, and then we have answered the question. Now let's see what the z value here is. So what we do is we take the normal distribution table and we have to look at it from the left hand side, right? We have to look at it from the left hand side because we are interested in this side. So we see where we get 0.025 in these numbers, and you will see that 0.025, I have already marked it here, is here. So the corresponding row value is minus 1.9 and the corresponding column value is 0.06, which means this value is minus 1.96. So that is how you figure out the z value. So since this is symmetrical, this value here is plus 1.96. Now we simply substitute it to this equation in order to figure out, let's call this x bar L, the lower value. We need to figure out this value, the corresponding value, and we need to figure out x bar H, let's call it the high value, right? So x bar L would be mu x bar is 368, and here z is plus z is minus 1.96 into sigma is 15 divided by n, the sample size is 25, root 25. When you calculate this, you will get the answer as 362.12. So the corresponding x bar value is 362.12 for x bar L. X bar H is again mu x bar is 368 plus, now the z value is plus 1.96 into 15 over root 25. This value will give you 373.88. So which means that 95% of the sample means of sample size 25 are between 362.12 and 373.88. Right, according to what we did, now the interval contains 95% of the sample means, which means 5% is outside the interval, and since it's symmetrical, there will be 2.5 on each side, and the corresponding z value for 0.025 is minus 1.96 on your left hand side and plus 1.96 on your right hand side. Because it's symmetrical, you have converted it into a standardized normal distribution, and you calculated your corresponding lower and upper limits, and you say that 95% of the sample means of sample size 25 are between these two values, right? This is the interpretation, and it is very important to write your interpretation in this fashion, right? So we were talking about sampling distribution of the mean when the population is normally distributed. Now let's have a look at when the sampling distribution of the mean when the population is not normal. So in that case, you have this theorem, very important theorem called central limit theorem. So even if the population is not normal, the sample means from the population will be approximately normal. That's a key term here, approximately normal, as long as the sample size is large enough. Now, this is very important. The central limit theorem tells you even if your population is not normally distributed, your sample means from the population will be approximately normally distributed. However, there's a condition, your sample size should be large enough, right? So basically, in that case, your mu x bar would be mu and your sigma x bar would be sigma over root n. So there's a video here that I have attached which explains this central limit theorem, right? Please do watch this video and you will get a better understanding of this central limit theorem. Now, here we are going to talk about if it's not normal, right? You have your central tendency or the mean of the sample mean equaling your population mean and your variation as well. So the population distribution is not normally distributed, right? And your sampling distribution, if the sample size is large enough, right? So this is an example of a smaller sample size. You would notice that it is not exactly normal, but as your sample size grows bigger, it would become more and more normally distributed, right? That is important. So if you noticed in that central limit theorem, what it said was even though your population is not normally distributed, your sampling distribution would be approximately normal if your sample size is large enough. Now, what do you mean by large enough? That is a very vague term. So as a rule of thumb, they say if your sample size is greater than or equal to 30, then your sampling distribution would be approximately normal. So that is an important point to keep in mind, right? So when you are given your examples, first check whether your population is normally distributed. If your population distribution is not told, then clearly you don't know the distribution of the population. In that case, check what the sample size is. If it's greater than 30, then you can use the central limit theorem, from which you can derive that your sampling distribution is normally distributed, and from which you can convert that sampling distribution into a standardized normal distribution and get whatever that answer that is required. So let's have a look at an example for this. Suppose the population has mean mu equals 8 and standard deviation sigma equals 3. Suppose a random sample of size n equals 36 is selected. What is the probability that the sample mean is between these two values? Right, here you're not told what the distribution of the population is, but you're told the mean of the population, which is 8, and the standard deviation. Notice that your sample size is 36, which is greater than 30. Now the question asks, what is the probability that the sample mean is between these two values, right? So let's have a look at the solution. Right, so how do we solve this? They're asking what is the probability that the sample mean is between these two values. So you don't know anything about the distribution about the population. You have no idea. But you're given the mean and the standard deviation. So first and foremost, note that n, the sample size, is greater than 30. That is important. So that was what we were studying. And then we also have that mu x bar, which is the same as mu, is 8. And also sigma x bar, which should be calculated, is sigma over root n. So sigma is given as 3 and sample size is 36, root of 36, and you would get 0.5. Right, so these values are important. Right, so what are we asked for now? We are asked for the probability that x bar lies in between the values 7.8 and 8.2. Let's convert this into the standardized normal distribution. So how would that change then? X bar would change as x bar minus mu divided by sigma over root 10. And the corresponding two values should also be changed in the same way. Mu is 7.8 minus mu is 8 divided by sigma over root 10, which is, we figured it out, 0.5. And the corresponding value of 8.2 would be 8.2 minus 8 divided by 0.5. So here we would get the probability of, here it's minus 0.4, and this value is the Z value, since we converted the original problem into a standardized normal distribution because we don't know the distribution of the population, and this value would be 0.4. So what we have here is we have some unknown population distribution which we have converted into the standardized normal distribution, where in the standardized normal distribution mu is 0 and we have the two values as minus 0.4 and plus 0.4, right? And we are asked to find the probability of the sample mean being in between these two values, which means since we have converted it, to find the probability, or in other words the area under the curve over here, right? So how do we do that? It's very simple. We figure out what are the corresponding values here, that is the area under the curve. So we know the Z values, right? So simply figure out the Z values. So we know the Z values. We go to the table here, and for plus 0.4 we have 0.6554, right? For plus we have 0.6554. What is this 0.6554? From the left hand side all the way up to plus 0.4, the area under the curve, this total area, it's 0.6554. But we don't need this particular area. We have to delete this particular area over here. So how do we figure out the area here? Well, it is negative 0.4. So go to the negative side. Negative 0.4 is 0.3446, right? Over here it is 0.3446. We have to deduct that 0.3446 from this value and we will end up with 0.3108. So the probability that X bar will lie in between these two values is 0.3108. Right. So you notice that your population is not given, which means you can safely assume it is not normally distributed. You also notice that your sample size is conveniently greater than 30. Not conveniently, but actually you should make sure that your sample size is greater than 30, because then you can use the central limit theorem and approximate that your sampling distribution is normally distributed with mean mu x bar of 8, because remember mu x bar is equal to mu, hence it's 8. Sigma x bar is sigma over root 10, your given sigma, which is 3, and you get the sigma x bar as 0.5. And accordingly you calculate the probability of x bar being in between these two values as 0.3108. What is important is the visualization. Now, population distribution, you have no idea. That's why I put question marks here. But you do know the mean, which is 8. So, since the sample size is greater than 30, the sampling distribution you can safely assume is normally distributed thanks to the central limit theorem. And your mu x bar would be 8. Because mu equals mu x bar, from which you are asked to figure out the probability, or in other words the area under the curve for x bar which lies in between these two values. We are talking about x bar. Then when you standardize this, you have Z and you have your standard normal distribution curve. Your mu of Z is 0 and your corresponding Z values would be minus 0.4 and plus 0.4. So see the sequence, how it has all played out. You have a population distribution which you don't know, but your sample mean is 8, right? Your random variable is X. You derive 36 samples from this and you plot your sampling and you derive the sample means of each of these samples and you plot your sampling distribution. Accordingly, you get this, and from that you get your standard normal distribution in order to calculate the probability of X bar lying in between these two values. Right, so up to now we have been talking about sample means. That is, we've been talking about sampling distributions, but more specifically we have been talking about the mean. Now we are going to talk about the proportions. So we use the symbol pi to note the proportion of the population, right, having a certain characteristic of interest, and we use the symbol simple p to denote the sample proportion, which is an estimate of your population proportion pi. So your sample proportion is given by x divided by n. X is the number of items in the sample having that particular characteristic of interest, right? The number of items in the sample divided by the sample size. So your simple p, or your sample proportion, it's a proportion, so therefore it lies between 0 and 1. P is approximately distributed as a normal distribution when n is large. So P is approximately distributed as a normal distribution when n is large. So you understand it's always good to have a large sample size, because that makes things easier, because your distribution, you can assume that your distribution is approximately normally distributed, even in the case of sample means or even in the case of sample proportions. So the sampling distribution of P, it is approximately normally distributed given that these two conditions are met. Your sample size into your population proportion should be greater than or equal to 5, and your sample size into 1 minus your population proportion should also be greater than or equal to 5, and your the sample mean, or the mean of the sample proportion, is equal to population proportion, and the standard deviation of your sample proportion is equal to this square root of your population proportion times 1 minus your population proportion divided by your sample size. Notice how you say this. This here, mu of P, is your mean of the sample proportions. Sigma of P is your standard deviation of the sample proportion. So pi is your population proportion. So if you were to draw this in a graph, you have simple P, which is your sample proportion, which lies in between 0 and 1, and your capital P, which is the probability of your sample proportions. So it would look something like this, given that these two conditions are met. So it would be approximately normally distributed. And the corresponding Z value for these proportions are given by this equation. Your sample proportion minus your population proportion divided by your standard deviation of the sample proportions. So let's have a look at an example. If the true proportion of voters who support proposition A is 0.4 population proportion, what is the probability that the sample size of 200 yields a sample proportion between 0.4 and 0.45? So in other words, they're asking for this. So let's have a look at the solution. Right, so how do we solve this? First, look at the question. They're asking for what is the probability that the sample size of 200 yields a sample proportion. So you know that this is talking about the sampling distribution of P, simple P, which is proportions, right? So you quickly write down that mu P is pi and sigma P is pi times 1 minus pi divided by n, the square root of this. So you write these things down. And you also write down that Z is P minus pi divided by sigma P. So sigma P is pi times 1 minus pi over n, the square root of this. Right. So they're saying that pi is 0.4. Pi is the true proportion of voters who support some proposition, something, is 0.4. And you're given that the sample size is 200. And what they're asking is the probability of the sample proportion, simple P, this is capital P, the probability, this is simple P for sample proportion, is in between 0.45 and 0.4, right? In between 0.45 and 0.4. So this is what they're asking for. So first and foremost, we figure out what sigma P is, right? So sigma P is pi into 1 minus pi divided by n, the square root of that, which is 0.4 into 1 minus 0.4 divided by 200, the square root of this, which gives me 0.03464, right? Now, as usual, let's convert this original problem into the standardized normal distribution. So the probability of simple P being in between 0.4 and 0.45 is converted into the standardized normal distribution, so that using this equation over here, simple P is now P minus pi divided by this value over here, which is sigma P. I'll just write it as sigma P. The corresponding other two values, 0.4 would be written as 0.4 minus pi is also 0.4 divided by sigma P, we figured out now, is 0.03464, and the corresponding value of 0.45 would be written as 0.45 minus 0.4 divided by sigma P, 0.03464, right? So the value here is 0, 0.4 minus 0.4 is 0. This is Z, and here you have 1.44, right? So accordingly, if you draw always remember to draw the curve, because that gives you some perspective, right? So corresponding value here is 0, and you have corresponding value of Z here as 1.44, right? So what they're asking for is the area under this curve over here between 0 and 1.44. So you take your normal distribution table and you look at 1.44, right, and see up to that point what is the area under the curve. So 1.4, and the corresponding column should be also 1.04, which gives you 0.9251, right? So from the left hand side up to 1.44, the value is 0.9251, but we don't need this area. What do I mean by this area? We don't require this area, since this is symmetrical. Since we are talking about standardized normal distributions, this area is 0.5, right? So when you deduct that, you get 0.4251. So 0.4251 is the area under the curve over here, or in other words, the sample proportion which lies between 0.4 and 0.45. Right, so in the solution, first you have to figure out what your standard deviation of your sample proportion is. That's what we did first. And then you converted your problem into standardized normal distribution, and such that you want to figure out the probability of Z being in between these two values. Hence, from which you derived the answer as 0.4251. So what you have to look at is the graph. So you have the sampling distribution of proportions, which is approximately normal, and your sample mean is 0.4, and you're asked to figure out the area under the curve in between 0.4 and 0.45. Now remember, this is your mean of the sample proportion, right, mu of p, which is also equal to your population proportion pi. So then you convert this sampling distribution into standardized normal distribution. Notice how this is simple p, sample proportion, and this is Z. And you have a standardized normal distribution. And here the corresponding 0.4 value of p is 0 in your standardized normal distribution. Your corresponding 0.45 value would be 1.44. Right? So the area under the curve here, shown in red, is given by the value which we figured out earlier, 0.4251. So the section summary, this was a very long section. We talked about probability and non-probability samples, that is in the first section, and then we talked about survey in the second section. Then we talked about sampling distributions. We talked about sampling distribution of the mean, right? That was the initial part that we talked about, and we talked about the mean for normal populations and for populations distributions which are not known, where we use the central limit theorem. And we talked about the sampling distribution of a proportion, and finally calculated probabilities using sampling distributions. Now let's have a brief introduction into this fourth section, which is sampling from finite populations, right? So in this case, we have something called finite population correction factors, right? So this is used to calculate the standard error of both the sample mean and the sample proportion. It is needed when the sample size n is more than 5% of the population size, and the finite population correction factor is given by this equation, right? So using the finite population correction factor, you calculate your standard error, which is given by this equation, and this is for the standard error of the mean and the standard error of the proportion for finite populations, right? So this correction is always less than 1. That is important to note and keep in mind. Let's have a look at an example. Suppose a random sample size of 100 is drawn from a population size of 1000. So instantly you know that it is the sample size is more than 5% of your population size, and your standard deviation is 40. So n is 100, your population size is 1000, which gives you 10%, which is greater than 5%. So using the FPC for the standard error of the mean, we get 3.8. So this is an example. You just have to be a little, you don't have to know in detail about this, but be aware of such a thing, right? That's what is important. So the fourth section, we looked at sampling from finite populations. This was a very important chapter which looked at 4 sections: sampling, survey, sampling distribution, and sampling from finite populations. The most important section of this chapter 7 was this third section of sampling distribution, where we talked about sampling distribution of mean and sampling distribution of proportion. And under sampling distribution of mean, we had 2 sections where the population is normally distributed and the population is not normally distributed. So in that case where the population is not normally distributed, we use the central limit theorem. And then we had the sampling distribution for proportions. Right, so the chapter summary, we looked at sampling, And then we looked at surveying, and we looked at sampling distribution, and we looked at some of the properties pertaining to sampling distribution, and then finally we looked at sampling from finite populations. Again, a quick reminder of the reference book. Please make sure that you download this and you do the problems, examples given in this particular book. And I've also included the video pertaining to this explanation in your PowerPoint, right? Make sure you go through that. And that is it for today. Thank you very much. And as always, dream big and start small. Thank you very much.